What's going on, guys? Mr. Jones coming at you once again. Today we're going to do Ready, Set, Go 4.2. So the ready portion is always something that you were supposed to have learned in the past, and we're just kind of retouching on it. But I'm not sure if you guys learned much about absolute value. Hopefully you know that whatever the absolute value is always has to be a positive number, right? It has to equal positive. So no matter what's inside here, even if that's negative, um, then you still get a positive answer. For example, if this is -3, the absolute value of -3 is 3. Or the absolute value of 3 is 3. So no matter what you put inside there, whatever your answer is, you always have to make it positive, and that's what absolute value is. So hopefully you guys remember that from school. If not, make sure to look it up. It's called absolute value. Okay, absolute value. This is really just talking about the distance away from something. So you can't really go a negative distance. You're just going a positive distance in the negative direction sometimes. Okay, so with that being said, since we know everything in the absolute has to be positive, the very first thing we have to realize is we're going to treat the absolute value like a variable. Treat like a variable. And basically, it's the variable that you want to solve for. So you want to basically get the entire absolute value by itself on one side of the equation, just like you would x in any other situation, right? So I'm going to rewrite this. And we're going to go ahead and do what we got to do to get the absolute value by itself. Okay, so the first thing I want to do is add 7 to both sides. And we get 2 absolute value x plus 1 equals 4. And now we have to divide both sides by 2. And we get the absolute value of x plus 1 equals 4 divided by 2 is 2. So now we just have this. Okay, this is what we have. We have gotten the absolute value by itself. Now we have to break this into 2 equations. One of them, and drop the absolute value at this point. So one of them is x plus 1 equals 2. And then the other one is x plus 1 equals -2. So really, you just turn whatever's on the other side positive, and then you turn it negative, and everything inside the absolute value stayed the same, right? So we just turn it into 2 equations, dropping the absolute value, and making the other side of the equation positive and then negative. It has to start off positive, though, because the answer can't actually be negative if it's in absolute value mode. So the absolute value of x cannot equal -2, for example. But x can equal -2, right? So down here, we took off the absolute value. Now you just go ahead and solve these. Subtract 1 from both sides, x equals 1. Subtract 1 from both sides, x equals -3. And you always are going to have 2 answers. I say always, pretty much always, unless you're at the vertex. Okay, so solving this was exactly like a regular equation, except for you have to make one side positive and one side negative, and remember that it has to start off positive. And then number 12, I've already answered this question for you, but I'll let you answer it now in your own words or go back and see where I answered that question. And by the way, this was problem number 9. Problem number 9 I have done for you for free. You're welcome. All right, going on to the goods. The set portion always follows the task we've been working on. It says state the domain and the range of the piecewise function in the graph. Okay, and then it says use interval notation. The good thing is domain, remember, is all possible x values. Okay, so your domain is going to have your numbers like this probably, small, big, and your range is all y values, all y values. So your domain, your range is going to look like this, right? And you're going to have small, big. Okay, I don't want to do these for you, so let's go to Desmos and look at a different graph. All right, so right here in Desmos, I put in my own piecewise function. I even threw the red one's line and the blue one's a parabola. Then you can see I have the equations here and then the domain here, right? So we know domain is all possible x values. If I ask for just the domain, though, of this entire piecewise function, you can put it all together because it's continuous. It's all connected. So let's look at this graph, the red and the blue combined, and we're going to say, okay, the domain is all possible x values. So my lowest x value is right here at -3. And my highest x value is 5, right? So I go all the way to the left at -3 and to the right is 5. The range is very similar. Okay, the range is all possible y values. So how low does your graph go? My graph goes down to -3, but it goes up to 11. Okay, so the -3 we're talking about is that y is -3. And the upper end up here is at the 11 where y is 11. Okay, so that's how, and I put 1. Oh, this is 11. 11. Cool. All right, good stuff. So that's how you're going to do domain and range for these two problems. I'm not sure what numbers they are. I guess number 13, 14, 13 and 14, even though there's no numbers next to them. Oh, yeah, there are. They're right here, but they're just kind of hard to see. All right, the next one's down. It says, for each of the graphs below, write the interval that defines each piece of the graph, then write the domain of the entire piecewise function. Okay, so you have to write the interval first, and then you have to write the domain. So it gives you an example, and I think it calls this one right here number 14. It says, example, look at the graph number 14. Move left to right. Remember, that's how we always read our graphs, from left to right. It says moving left to right and use set notation, which is the notation that looks like this. So my graph right here, you can see starts at the -3 and ends at the 0. That's exactly what this one's saying. And then from the 0 to the 4, and then from the 4 to the 6. So all it's having you do is write the intervals. You don't have to come up with the equation. The entire domain is from -3 to 6. So my lowest value, which is my first graph, to my highest value, okay, which is my last graph. Okay, that's all it wants you to do for these ones, is say all three intervals and then say the entire domain. Number 17 says, so far you've only seen continuous piecewise functions. Continuous meaning it's all connected. But piecewise functions can also be non-continuous. In fact, you've had some real-life experiences with one kind of non-continuous piecewise function. The graph below represents how some teachers calculate grades. Finish filling in the piecewise equation, then label the graph with the corresponding values. So let's look and see what it wants us to do here. After looking at it, it looks like the numbers are all missing, so I'm not really sure what to do there because it looks like it's cut off somewhere, and so the curriculum needs to do a better job. So, let's go back. That was a mistake. So with that being said, we're going to go ahead and skip that problem. Let's let this load back up here. All right, skip number 17. Let's go ahead and write that. Skip number 17. So I'm probably not going to write it in the directions, but if you watch the video, you'll skip it. This is how I know students don't watch my videos, because they don't do this part, skip stuff. All right, 18 and 19, you're going to go ahead and write piecewise functions. The difference is that they're disconnected. So if there's a gap, then there's going to be a gap in your domain, right? This domain starts at the 0 and goes to the, 4? But then the next graph comes and picks up at the 5. Notice they're both closed dots, so they should have the inequality symbol like these ones. Okay, if they're open dot, they just have an inequality symbol like that. So 18 and 19 you should be able to do. On those problems, I expect to see your work, okay, first of all, and it should look like this, right? Equation, and then domain, and then you're going to have them separated by commas, right? And each 18 and 19 should both have two equations. All right, and then the go section, we're almost done. It says begin with the parent function, f of x equals x squared. That's the parent function of a parabola. Write the equation of the new function g of x, that is a transformation of f of x, as described, and then graph it. All right, so let's look at number 20. I'm going to see if I can do number 20 for you guys, and you can do the other two. This one seems pretty crazy. So start off with the regular parabola, f of x equals x squared. So remember, that's normally has a vertex here. And then it says shift it 3 units to the left. So now my new vertex will be here after I've shifted 3 units to the left. And then stretch it vertically by 2. So we know we're going to have a stretch of 2. Okay. Stretch of 2. And then it says reflect it vertically. So now instead of going up, it's going to go down. So really a stretch of -2. Okay. And then shift it down 5 units. So 1, 2, 3, 4, 5. So now here's my new vertex, right? This is my final vertex. Okay. Normally my graph goes over 1, down 1, for example, but this time, since the stretch is 2, we have to go over 1, down 2, over 1, down 2, and then you can basically draw your parabola. Okay. So there's my sketch. And then it says, what's the equation? Well, the normal equation was y equals x squared, but my new vertex is at -3, -5. Okay, -3, -5 with a stretch of -2. So I could write it in vertex form. Here's my stretch. Here is my shift to the left, and here is my shift down. And there is my new equation. So let's bring back those skills. Look up how to write an equation in vertex form if you need to. But there's number 20 done for you and graphed. Now you guys can do 21, 22. All right, guys, let me know if you have any questions. Have a great day.